My name is Helen Miles. I'm a computer scientist working at Aberystwyth University, and part of a small team from the Departments of Physics and Computer Science working on the European Space Agency and Roscosmos Exomars Mission to search for evidence of life on Mars. In this video, I'm going to tell you a little bit about the Exomars mission and what we're doing as a part of it. Exomars, short for Exobiology on Mars, is a two-part mission to search for signs of past or present life on Mars. Part 1, the Trace Gas Orbiter, was launched in 2016 and reached a stable orbit around Mars in April 2018. Part 2, the Rosalind Franklin rover and the Casa Choc lander platform, is scheduled to launch in 2022. The Rosalind Franklin rover is a six-wheeled rover as big as a car. It's solar-powered and carries a suite of scientific instruments to enable scientists to remotely search for signs of life. Aberystwyth University are part of 3 rover instrument teams. The panoramic camera PanCam, an instrument led by UCL's Millard Space Science Laboratory in Surrey. The infrared spectrometer for Exomars, ISEM, led by the Russian Academy of Science at the Space Research Institute. And the close-up imager CLUPI, led by the Space Exploration Institute. PanCam is the primary remote sensing camera system on the rover. It will be used to search for places to investigate. PanCam can pan and tilt to look around in all directions and contains 3 individual cameras, 2 wide-angle cameras, WACS, and the high-resolution camera, HRC. The wide-angle cameras are multispectral. The cameras themselves take monochrome images, shades of grey, but in front of each camera is a filter wheel containing 11 different filters, each with a different purpose. Some of them allow us to take colour photographs, while others let us see into the infrared, showing us things our eyes can't see, like minerals which can only be made where there has been water. A good place to search for evidence of life. Exomars is a huge mission involving many people from all over the world. Aberystwyth University's contributions are developing and manufacturing hardware for PanCam, ISEM and CLUPI, calibrating PanCam and ISEM, helping to develop the processes to use PanCam, modelling and visualising the images produced by PanCam, and developing software to process the real images from PanCam. Calibration is the most important thing we can do with the cameras. Without calibration, we have no scientific measurements.
We have to calibrate camera systems, otherwise the pictures we get are not meaningful in any scientific way. Cameras are never perfect. There's always something that causes distortions in images or colours to come out wrong. So how do we make sure things are right? Well, on Earth we use colour checkers, things like this, or geometric targets that allow us to make sure that that the camera is showing what's really there. So this has 6 different grayscale levels and 18 different colour patches, and each of the grayscale levels is very well characterised along with all the colour ones, so we know exactly what colour each of the patches are. And using that information, and you can look at a picture that the camera's taken, and you can then work out how to adjust it to make sure everything's perfect. Using the measurements that we get from the test targets and clever software, we can turn the images into useful measurements. We took part in a major calibration campaign to learn as much about the cameras as possible. For radiometric calibration, we're trying to understand how the cameras respond to light and to dark. So we take hundreds of photos of a completely plain white background or a completely plain black background. If the background is uniform enough, then this allows us to see all the little features of the camera that are not quite right. So if one pixel is more sensitive than the others, then that'll show up. If one pixel is not less sensitive than the others, then that'll show up. Calibration is one of the last things that we do. It doesn't have to be the last thing, but you have to make sure that nothing gets changed on the camera between calibrating it and landing on Mars. So the whole rover is kept very clean and very sterile, and some of the things that we need to calibrate can only be done on the fully assembled rover, so we have to go and work with it. So the calibrations that we do on Earth allow us to work out how the camera responds to light. The calibrations we have to do on Mars are to tell us what the light is like on Mars. So on Earth, light is sort of bluish, so the sky is blue. On Mars, the sky is red, and the light is much sort of redder, so we need to characterise all of that, and we do that by taking calibration measurements when we get there. So this is the calibration target for PanCam, which will be used on the Exomars rover. It's made of aluminium and stained glass. It provides us with several reference patches, which we know exactly what their colour and sort of reflectance properties are. So this is basically what we will use for getting all the colour measurements on Mars. So these are fiducial markers. They are geometric reference points that will be used on the rover. So we need a few points where we know exactly where they are, and that they're easy to identify, so we can make sure that the camera and the Mars system is all calibrated correctly. This is the rover inspection mirror. It allows us to see bits of the rover that you couldn't see otherwise. So we can basically use a mirror. It's basically like having a mirror on a stick to look underneath the rover.
After years of development and manufacture, the small items are now all attached to the real rover. Understanding how to use any instrument effectively is really important. Imagine going for an exciting day out with your new camera and only finding out later that all the photos you took were blurry. With your camera not allowed to leave a clean room, it's very tricky to learn how to use it. So we've been working on some ways to help. Meet UPI. UPI is the Aberystwyth University PanCam emulator. It's made from off-the-shelf components, is a lot bigger than the real thing, and definitely isn't space qualified. But it produces images which are very similar to those that will come from the real PanCam instrument, and has been made to go into the field. It has travelled with scientists to Mars analogue sites all over the world. It's important for UPI to photograph different kinds of rocks and minerals in different environments, to help scientists understand what they can expect to see from PanCam, and how to make the most of the data that comes back from Mars. The data from UPI have been used to develop processing methods, ways of manipulating the data and combining the data from different filters that highlight particular minerals. UPI has been used in several rover field trials, scenarios which let scientists and engineers practice for what the real mission will be like. A rover emulator is taken to a secret location and looked after by one team, while another team work together in a control room to try to work out where they are and to understand what geology is around them. The team in the control room send instructions to the rover, where to go and what to measure or take images of, and a team in the field provide that data. The two teams can be on different sides of the world, and the field trial can last for several weeks. It takes a long time to do anything when you have limited information. You might have noticed that the rover emulator is not quite like the real thing. The real rover is so complex and expensive, it isn't possible to make a duplicate to go out for field trials. Now this leaves us with a gap in our understanding. How can we be sure that the real rover can see the calibration target or the rover inspection mirror? The ideal solution would be to use the real rover to take test images before launch, but because of the tight schedule for building the rover, this hasn't been possible. Instead, We can use computer graphics to simulate the views from the cameras, using the same techniques as are used to make images or videos of what the rover will look like, and the same that are used in the film industry. We can look through the eyes of PanCam. This can help us solve some really important problems. Where should PanCam be pointing to get the best data from the calibration target, or the rover inspection mirror? Can PanCam see all of the fiducial markers clearly? The rover is able to pick up core samples using a drill on the front. Can PanCam see the core before the drawer pulls it into the internal laboratory? Using this simulation system together with UPI allows us to better understand the output of the camera system. So now we have calibration measurements for individual camera properties and an understanding of how to use the PanCam system. But once we land on Mars, we need to use all of this information to ensure that the images used for scientific analysis are as accurate and free as artifacts as possible. Some pixels won't give the most accurate data because of the way current flows in the sensor, the way lenses collect light, pre-existing imperfections in the sensor, and some pixels will become damaged by X-rays or cosmic rays during the mission. The calibration done before launch will help us to mitigate some of these points, and the continuous calibration during the mission will help us to update our information and track changes to each pixel over time. By creating software to process each pixel of the image according to its own specific needs, we will be able to create higher quality data for scientists to use. But there is a complication. Mars is a very dusty planet, and once we arrive, the rover, camera, calibration target will all slowly start to get covered with dust. We need to learn more about the optical properties of dust on Mars and how the light and dust will change what cameras will see. This is our next challenge. This is ongoing work, and we're still in the process of analysing the calibration data and developing the algorithms for the software. Once it is complete and the mission starts, any images from PanCam will go through this software to ensure data of highest possible quality before being used for scientific analysis. So what's next for the Exomars mission? Launch is scheduled for 2022, which would see the rover land mid-2023. After that, the mission aims for at least 218 sols, Martian days, of science. But the NASA Opportunity rover was expected to last 90 sols and continue to run for 15 years. Hopefully Exomars will have similar success. The Exomars mission involves a lot of people and is a very collaborative project. Our work would not be possible without others. We want to give special thanks to the late Professor Dave Barnes, who set this all in motion and is greatly missed. To find out more about our work, visit exomars.wales or exomars.cymru. To learn more about the Exomars mission, visit www.esa.int.